All right, dummy variables. Let's jump into this one. We will work on slides 1 to 14, and I'll do a part 2 with the remaining slides. I will try to keep this very short, although I'm not making any promises. Anyway, so the first thing we'll look at is we have some data, we have some qualitative information in the data, and we're trying to incorporate that qualitative explanatory variable into a multiple linear regression. So how do we do that? Yeah, I'll jump into that soon. Then we'll work on naming our dummy variable. It's important to name it in a more specific way so that we know which category takes a 1 and which category takes a 0, right? We'll jump into that. Now, if the dummy variable has 2 categories, it can have more than 2 categories. But if it has 2 categories, you can derive 2 equations from the econometric model or from the associated econometric model for each category. And then we'll jump into interpretation of coefficients on the dummy variable that we always compare to the base category. Of course, we fix all other variables and we add on average, right? We'll look at a graphical illustration and we'll talk about the dummy variable trap, see some examples, and call it done for this part 1. All right. So here is a data set. We have wage, education, and gender at birth. And so very quickly, let me add in some useful information so we can get this started. Let's say we have here the first individual has wage 20K, education 12 years, gender at birth female. Now I'm just making all of this up, right? Second individual, wage is 50K, education is 13 years, gender at birth is female, and on and on and on. Individual 3, how about 60K, 14, gender at birth male. Individual 4, 120K, 16, gender at birth, let's have male. Individual 5, 160K, 18, gender at birth female. And we have this going on and on and on until individual 1000, right? We have 80K, 15 years, and gender at birth female. Okay, so the qualitative information here is the gender at birth. We are interested in creating a dummy variable, and we'll create one so that it appears in the data set. And this all depends on how we name the dummy variable. If we name the dummy variable female, right? If name dummy variable female, well, why can't you just name it gender? Okay, you can. However, if you're looking at this some months later, how do you know which category is a 1 and which category is a 0? Now, what do I mean by that? Let's take a look at the information on qualitative data. Well, the dummy variable is used to capture some yes or no information, right? It's also known as a binary variable or a 0-1 variable. So we capture information on gender at birth, race at birth, a person owns or does not own a computer, a firm offers or does not offer 401k plans. So, well, dummy variables can appear as the explanatory variable or the response variable. And so if you had the qualitative data, gender at birth, and you were trying to get a dummy variable which was more quantitative so that one category is 0 whilst the other is takes a 1. If you name it gender, it's hard to remember which category, either male or female, that took the 1 and which one took the 0. And so if I name my dummy variable female, that is obvious that female took the 1, right? 1 applied if female, 0 otherwise. And so in the data example right here, how about I write, let's use a different color so that it pops at us. Let's use red. If I have female here, then wherever I see female, I apply a 1. So female in the first row gets a 1, second row a 1, third row a 0, fourth row a 0, fifth row fifth row a 1, and then the 1000th row a 1. Do you see that? Cool. Now, if I decide that, well, I want to name my dummy variable male, then that means I apply a 1 if male, 0 otherwise. And so let's use blue here. Okay, in the first row it says female, so 0, 0, 1, 1, 0, 0. Right? So that's how to get the gender at birth column into, or generate a dummy variable from the gender at birth column. Now, I know I have written both female and male into the data set here, but do you put male and female variables into your econometric model? No. And we'll talk about that in a minute. But let's look at the econometric model that's associated with this data set that we're working with. Well, we have wage as a response variable equals beta 0, the intercept, plus delta 0. Delta 0 is the parameter on the dummy variable female, plus beta 1 times education plus u. So this is the econometric model. This tells you that I am going with the female column as my dummy variable. If you notice, I didn't put the male in there. Why? Because male and female are perfectly collinear. The male and female columns are perfectly collinear. If I put them into my econometric model, I will run into multicollinearity issues. In fact, if you do this in R or Stata, Stata may drop 1 and keep 1 for you. R might throw some errors at you, and that should prompt you to take one of the variables out. All right, take one of the dummy variables out. So if you have gender, which has two categories, you have to drop one of the categories. What if you had 4 categories? You always drop one of the categories. Okay, cool. All right, so from this econometric model, we can derive a male wage equation, and we can derive a female wage equation. So let's work on that. The male wage equation will be wage equal beta 0 plus, well, delta 0 female. Now, with your female dummy variable, because you named your dummy variable female, it took a 1 when it was female but 0 otherwise. So, well, plus delta 0 times 0 plus beta 1 education plus u. Now this goes to wage equals beta 0. That's 0. Well, delta 0 plus 0 times 0 is 0, plus beta 1 times education plus u. And so the male wage equation is this one right here. That's the male wage equation. The female wage equation, and I'll change colors now to red. The female wage equation is this one, beta 0, wage equal beta 0 plus delta 0 times 1 plus beta 1 times education plus u. And from here, we have wage equal beta 0 plus delta 0. I'll put the 2 into parentheses like this. Yes, beta 0 plus delta 0 is now the intercept for the female equation, plus beta 1 times education plus u. So the female equation is this one. We can graph this. If you notice, the male intercept is just beta 0, and the male slope is just beta 1. Now, the female intercept is beta 0 plus delta 0, and the female slope is beta 1. How do we draw this? Well, delta 0 is going to be negative. And so when we draw this, I'll draw the female one first. Beta 0 plus delta 0, where delta 0 is a negative value, the beta 0 will drop down, right? So it will start lower. So this is beta 0 plus delta 0. And then the slope, beta 1, be like that. The slope of this red line is beta 1. Now, for the blue line, drawing the male wage equation, where we have education on the x-axis and wage on the y-axis, beta 0 is up here. Now they have the same slope though, so I have to draw a line that's parallel to the red one. Now I'll do my best to make sure my blue line is parallel to the red one. And the slopes of these two, slope is beta 1 for the two lines here, you see. Let's go back to the slides and look at things. So what we just did is up here, where it's always better to name your dummy variable a specific name, which takes the 1 and a 0 otherwise. So if you could name it male, if you name it male, then whenever in the qualitative information it's a male, it takes a 1, otherwise it takes a 0, like that. And if you name it female, then from the qualitative information, wherever it's a female, it takes a 1, otherwise it takes a 0. Right? So this is your econometric model here. Your econometric model could have been written as this too. Okay. And so this is what I just worked on, where I took that econometric model where we used the female dummy variable and we derived the female equation and the male equation, and we noticed that the female intercept was beta 0 plus delta 0 and the male intercept was just beta 0, and the difference between these two in the intercept was delta 0. In the slopes, there was no difference because the slopes were the same, beta 1. So when you try to find the difference in hourly wages between males and females given the same level of education and the same error term, then we would write it mathematically as so. The expected value of wage conditional on female being 1, where education is fixed, minus the expected value conditional on female being 0, with education being fixed, is delta 0. So if your delta zero is negative, and from my drawing, I assumed that delta zero was negative, then on average, women would earn less than men with the same level of other factors like education. Now, that meant that when we drew the male and the female equations, the female equation started at a lower point, right? The intercept for female was lower than the male intercept. So again, the dummy variable coefficient delta zero for females in this case represents the estimated difference in intercepts between the females and the base group males with the same level of all other factors such as education. Now, I had made mention of the dummy variable trap, that if you were to put male and female into your econometric model like what it looks like right here, if you were to do that, the model cannot be estimated because there is perfect collinearity. These two, male and female, are perfectly collinear. If you sum them up, do you see how you'll get 1? The female right here plus the male, right? That's a 1. Right? So if you keep the two of them in there, the model cannot be estimated. Now, cast your mind back to multicollinearity. That's exactly what I'm talking about. So, when using dummy variables, if you have 2 categories, one category will always have to be dropped. What if you had 5 categories? One category is always dropped. What if you have 10 categories? One category is always dropped. Okay. So in this first equation where we have a female dummy variable, that means that we left out the male category, or making the male category the base group or the base category. Okay, and where you have the male dummy variable in there, then the base category that we compare to is the women category. Now, one could omit the intercept, but if you do that, it's difficult to test for differences between the parameters, and your R squared is not valid anymore without an intercept. How do we interpret the estimated coefficient on the dummy variable? Well, right here we have delta 0 equal negative 1.81. How do we interpret that? Well, you say, holding all other factors constant, if female compared to the base category, male, wages would fall by $1.81 on average. If female compared to male, holding all other factors constant, wage falls by $1.81 on average. So in the interpretation, you say on average, you say holding all else constant, and then you compare to the base category. Now, this negative $1.81, does that mean women are being discriminated against? Well, let's go to the next slide for a minute, and I'll talk more about that. Assuming you do not include any other factor such as experience, like we had here. We had experience and we had tenure and education. So if you exclude these other factors, you'll notice that our delta 0 gets bigger. It becomes a bigger negative number, right? It widens the gap in wages between men and women. So this means that the more you control for relevant factors, the smaller your delta 0 gets in absolute value. Okay. Again, the wage difference between males and females is larger if no other no other things are controlled for, no other variables are controlled for. Like we controlled for education, experience, and tenure earlier on, where we had a gap of $1.81, and here we have a gap of $2.51 when we do not control for any other factor. Are women being discriminated against? Well, I posted some articles by Claudia Golden that dives into some of these topics. So I'll leave that reading to you so that you can see for yourself what is happening in this. It's highly discussed in labor economics. Let's see the last example and we will call this video done. Okay, so the next example is linked over about 3 slides. So I'll go to the last slide, which is slide 14. We are looking at the effect of training grants on hours of training. So we have hours of training per employee equal some intercept plus some beta 1 hat times grant. What is grant? Well, the grant is the dummy variable which takes a 1 if a grant is received and takes a 0 otherwise, right? And we multiply, we add in onto that another estimated coefficient times log of sales plus another estimated coefficient times log of number of employees, right? That's what we have here. And we have estimated the model and found our estimated coefficients. So is the treatment or is the effects of the treatment on the outcome of interest a causal effect? The answer is no, this is not a causal effect. That if so, how do we interpret this plus 26.25? If a grant is received compared to otherwise, then hours of training per employee increases by 26.25 hours on average, holding all else constant. Now, why is this not a causal effect? Receiving a grant may be correlated with something else that we have not controlled for. In fact, it may be that some firms who are receiving the grant would have trained their employees anyway in the absence of the grant. You see, so this is not a causal effect. But our studies, we are interested in interpreting that 26.25 and checking to make sure, yeah, this is not a causal effect. And that's it. So I'm done for this video. Let's take a quick look at what we just worked on. And I believe we nailed all our points today. Take your time and go through some of these things. You'll see them again in the part 2 of the video that follows this. And Dr. T out. For now, I'll be back with part 2. Thank you. Bye-bye. Like, share, subscribe.